Hi everyone, this is Satyajit Das, and in this video I'm going to do a deep dive of the Go-ethereum code base. So Go-ethereum is the execution layer or one of the execution layer clients of Ethereum, and I'm assuming you have basic knowledge of how Ethereum works, but here is a very quick recap. So I'm in this website called epf.wiki, which has decent information about how Ethereum works and how the various clients of Ethereum work. So Ethereum is essentially a blockchain which has two layers. So one of them is execution layer, another is consensus layer. So roughly how they work is the following. So the consensus layer is responsible for the consensus side of things, which includes the fork choice, P2P, blobs, and the validators. So the validators eventually propose blocks. And what does the execution layer do? Execution layer is in charge of storing the state, doing the EVM related things, and processing the transactions, storing them in the mempool, and doing P2P as well. And both of them talk to each other through this engine API. So Go-ethereum is the execution layer, one of the execution layer clients. There are several others, but originally it was only Go-ethereum, which used to have both consensus layer as well as execution layer. But after the merge, what has happened is that consensus layer and execution layer are separate now. So the consensus layer side of things are done by consensus layer clients, and Prism is one of them, which is written in Go. And the execution layer things are happening inside the execution layer clients, and Go-ethereum is one of them. Okay, so let's start exploring the Go-ethereum code base. So for any Go code base, the first thing you would like to find out is what's the entry point, which means where exactly is the main.go file is defined, so that once you run it, your entire program starts to run. So in this case, I have already cloned this Go-ethereum repository from GitHub, and inside this CMD folder, there are several other subfolders you can see. The important one here is Geth, which is the short form of Go-ethereum. And inside Geth, as you can see, there is this main.go file. So this main.go file has this init function, which does the initialization in any Go program. And here, this is the main function, which what it does is this app.run. So what is this app? App is flags.new app, and this new app, what it does is it creates this CLI.new app. So we are creating a new app which has certain functionalities. And what is this CLI? CLI is one of the imports here. So this is the CLI. Okay, so the all we do in the main function is app.run, but it is defined here. And inside this init function, what we're doing is we're assigning app.action and app.commands. So what sort of commands it can do? So these are all the commands: export command, init command, and each of these commands are of type CLI.command. And the important bit here is this app.action, which is it is an action function type. So in this case, this is assigned to Geth function, right? So this Geth function gets called when we do app.run. Okay, so inside this app.run, it calls run context, which eventually calls root command.run, and that eventually ends up calling this c.action, which is the action function. So eventually what we're going to end up with is simply calling this Geth. Okay, so this Geth is the main entry point into the system if no special subcommand is run. Okay, so by default we're running this Geth, and it creates a default node based on the command line arguments and runs it in the blocking mode, waiting for it to shut down. Let me zoom in a bit. Okay, and what does the Geth function have? So Geth has some initial preparation, but the important function here is that it calls makeFullNode, and which returns a node, essentially something of type node. I don't know why it is called stack exactly, but then eventually we do start node where we pass this stack. Okay, so we will explore first these two functions. So what is a makeFullNode and how do you start it? So makeFullNode, it returns something of type node.node, and node here, this is inside node package. So here we are in the CMD package. If we go down, there is this node package. Okay, so inside this package, this node struct is defined. And what is a node? Node is a container in which the services can be registered. So this is essentially the Ethereum node. And what all things does it have? It has P2P server. It has config, which is of type config. It has some HTTP servers, and it has databases. So inside this makeFullNode function, you first call something called makeConfigNode. And what it does is it loads a Geth configuration and creates a blank node instance. And then it does some registration stuff. So what it does is it calls this register ETH service. So what is it? So it sends config.eth. Okay, so what is this ETH? So here when we call makeConfigNode, it also returns something called Geth config, and inside this Geth config we have ETH, we have node, and we have some starts and metrics. So these two are important. ETH config is ethconfig.config, and this is inside ETH package. So we have a node package, as I mentioned, and we also have a ETH package, and that is in charge of doing all the Ethereum related stuff. So it has downloader, fetcher, gas price and stuff. So Ethereum node related stuff. So inside this config we have Genesis. So Genesis is the first block of a blockchain. So Genesis is of type core.genesis. We have network ID. So every blockchain has its own network ID to ensure that we can't replay the transactions from one blockchain to the other. And there's this sync mode, history mode, so various modes in which you can run. And this transaction history, transaction lookup, options related to database, options related to try. So try is a format in which the data is stored. And then configuration related to transactions, so tx pool, blob pool. Okay, so now when we have this config, we call this register ETH service, and what it does is that it uses that ethconfig.config to create a new ETH instance. So register ETH service adds an Ethereum client to the stack or the node, which I talked about. So this eth.node actually creates this Ethereum client, in which case it is our execution client. And the second return value is the full node instance. Okay, so here what it does is it creates this eth.new. So let's explore that. So eth.new is new creates a new Ethereum object, including the initialization of common Ethereum object, whose life cycle will be managed by the provided node. Okay, so this returns something of type Ethereum, which I showed before. So Ethereum, this is inside this backend.go, which is inside the ETH package, as you can see. So it is inside this ETH package, and here we have the backend.go. Okay, so this Ethereum struct, it implements the Ethereum full node service. Okay, so to run the full node, you need lots of things. So one of them is you need to keep track of transactions, which is done by this tx pool, which is of type txpool.txpool. And if we go inside this tx pool is a struct. So tx pool is an aggregator for various transaction specific pools. So there are multiple types of pools, collectively tracking all the transactions deemed interesting by the node. Transactions enter the pool when they are received from the network or submitted locally. So whenever you send your Ethereum transaction, they eventually end up in one of the transaction pools. Okay, and these are in memory in general, and they exit the pool when they're included in the blockchain or evicted due to resource constraints. Okay, so There will be some checks on your transactions. So if your transaction is valid, it is likely that it will be included at least in the mem pool, which is called the transaction pool. If it ends up becoming part of a block, that's great. Your transaction is successful. If not, then due to resource constraints, it might be evicted, in which case you may have to retry your transaction. Okay, so this is the tx pool struct, which is inside this Go-ethereum core txpool.go. Okay, so it is inside this. We are here in command folder. There is this core package. Inside that, there is txpool package. Okay, so inside this txpool, we have this txpool.go, and this is called package txpool. And this txpool struct has multiple sub pools. So what is a sub pool? Sub pool is an interface. Sub pool represents a specialized transaction pool that lives on its own, and it is independent of how many specialized pools we have. So inside a sub pool, there are certain functions. So filter to filter out the transactions, initialization, close, reset, set gas tip related to gas, has get using this get function you can actually get the actual transaction. This get RLP, get blobs. So there are like currently two types of transactions. One is the normal transaction which you send, another is the blob transaction. So the blob transaction returns the number. So this get blobs returns a number of blobs. So this get blobs returns the blobs and the corresponding proofs. And here the blob is of type KZG4844 blob. So if you know what is proto-dank sharding, which is a recent addition to Ethereum ecosystem. So this is part of Ethereum's scaling effort to support the layer 2s. Okay, so layer 2s are dependent on layer 1 like Ethereum to act as a single source of truth when it comes to data or proofs. And how a layer 2 generates its proofs, that doesn't matter to Ethereum. What matters is that layer 2 would like to store some data in the form of bytes inside Ethereum. Okay, it can be related to the proof data. And those are ideally stored in the form of blobs right now, which used to be stored in the form of call data, which was expensive. But then Ethereum came up with this idea of this transient data storage solution, which is called blobs. So each blob is of type, a byte slice or byte array, and there's a specific size to it. Okay, 128 KB, I think this is. So ideally, when the layer 2s are sending their proofs or data, they are sending it through a blob transaction. Okay, so this txpool struct has sub pools. So one of them is for blob transactions, as I mentioned, and it also needs to have the idea of what the blockchain is like, which is why it is storing this chain, which is of type blockchain. So let's explore what is this. So blockchain type interface. So blockchain defines the minimal set of methods needed to back a TX pool with a chain. Okay, so it needs to have enough information about the state of the blockchain so that the TX pool can judiciously check for transactions and then decide whether to include it in the pool or not. So this is in the form of interface, and it has these 4 functions. So it needs to know the current block, it needs to know the state at, and it needs to know some form of config which retrieves the chain's fork configuration. And there are 4 implementations to it. One of them is the actual blockchain. If I go into that, this is the full-blown blockchain struct, which is inside this core package again. So this core package is quite involved. It's a pretty huge package which has a lot of things. It has a TX pool, as I was talking about. It has VM, which I will explain later. It has types. So all the types which we normally have, like a block or transaction type, and it also has blockchain.go. Okay, so what is this blockchain struct? So blockchain represents the canonical chain given a database with a genesis block. The blockchain manages chain imports, reverts, and chain reorganizations. So it imports blocks from other nodes, and it does the processing. And blockchain also helps in returning blocks from any chain included in the database, as well as the blocks that represent in the canonical chain. Okay, so let's see what all stuff it has. It has this chain config and cache config. So chain config is the information about the blockchain settings. Okay, so it has the chain ID, which I mentioned before, and then it has a series of uh, something called blocks. Then it has a series of the hard fork blocks. So this Homestead block, Byzantium block, Constantinople. So these are all hard forks. Istanbul block, Berlin block, London block. So what used to happen is that the hard forks used to happen block wise. So that's why these are of type big int. So you just set from this block onwards we are doing a hard fork. But what has happened since the Shanghai hard fork is that it is in terms of time now. So the hard fork times are set using the actual time in the form of uint64. So Shanghai time, Cancun time, Prague, Osaka, Verkle time, and it has a few other settings. Some of them are not necessarily used. So like ETH hash, click, these who used to be the consensus mechanisms before, but now ever since the EL and CL are separate now, so the consensus side of things are mostly done by the consensus layer, not by Go-ethereum. Okay, so where was I? So this is the chain config which the blockchain struct stores. What else does a blockchain struct is supposed to store? It is supposed to store the database itself. So DB is of type ETHDB database, which is low level persistent database to store final content in. So this is the database interface, which contains all the methods required by the high level database to store the key value data. Okay, so the state of the blockchain which is stored, this is taken care of by this database. And it also has snapshots, the try DB. So a lot of database are stored in the form of tries, and this is where it is stored. Then there is the state DB. So state DB and try DB, two different types of database which we have. Then it also stores the current block. Okay, it's important to know what is the current block, what is the current head of the chain, so that you can check if a new upcoming block is part of the current block, or if it's part of a if it is part of the current currently accepted correct chain, or if it is part of a hard fork chain or a forked chain. Okay, and current snap block, which is a current head of snap sync. So if you're doing a sync, then you need to keep track of the head of that syncing process as well. And it has some caches and some channels to coordinate stuff. And it also has a consensus engine, validators. So these are two important things. So you need to have, for any blockchain, you need to have validators as well as a consensus engine. And these are again mostly done in the consensus layer, which one example is Prism. Okay, so I was in the TX pool struct, which has the reference to the blockchain itself. It has a signer. It has the reference to the state DB, the current state of the blockchain head. Okay, so these all information the TX pool struct needs to be able to validate the transactions and actually include it inside the mempool. Okay, so let's first dig into that for now. So this what's happening here is when you create this TX pool, you call this new function. Let me show you where exactly it is called. So if I simply check where it is called, I see this backend.go where txpool.new is called. and which is inside this new function, which is called inside this register each service, which is again called from this makeFullNode, which is called from this Geth function, which I originally showed you. Okay, so we know that at some point this txpool.new function is going to get called, and this what it does with for each of the subpools, it calls the init function, and then it does this pool.loop. Okay, so it initializes the subpools and it does a loop, and inside this loop what it does is it listens for new head. So if there is any new chain head event, which means the chain has progressed, then it listens for that. And if the new head and the old head are not the same, that means it is written something interesting might have happened. Run a reset if there is one needed, but none is running. The resetter will run on its own Go routine to allow chain head events to be consumed continuously. Okay, so if there is a new head event, then you reset it and you call the subpool.reset, where you give this was the old head, this is the new head, so do whatever you need to do to reset your head information. And yeah, that's one of the important things that happens here. Let's see, one thing we didn't check is the init function. Okay, so subpool.init. So how many subpools are there? So currently there are like 2 subpools. So one of them is for blob pool, another is for legacy pool. So let's check the legacy pool.go, which if you let's say send a normal Ethereum transaction where you are sending 1 ETH from one address to the other, it will end up in this legacy pool.go file. Okay, so this one has it's a pretty long file, but let's look at the init function first. Okay, so this is the init function. Init sets the gas price needed to keep a transaction in the pool and the chain head to allow balance and nonce checks. The internal Go routines will be spun up and the pool deemed operational afterwards. Okay, so whenever there is something, some init function is called for an important struct, always think in terms of it's most likely it's going to start a Go routine. Okay, so in this case it is starting a Go routine, which is a loop. So in general there's a loopy Go routine that starts, and inside that loop there must be continuous listening for anything new that is happening. Okay, so the loop is a transaction pool's main event loop, waiting for and reacting to outside blockchain events as well as for various reporting and transaction eviction events. Okay, so what it does is it creates it does an infinite for loop inside which it is checking if there is any shutdown happening, or there is a stats thing is happening, or if we want to evict a certain transaction. So one more function that should be used quite often is this add function. So let's see where it is called. Okay, so there is this add function which is called when we are supposed to add a transaction to our pool. So add enqueues a batch of transactions into the pool if they are valid. Okay, so this add function will be called at various times. If let's say your node gets a new transaction, then it is going to add it, or if it listens a new transaction from another peer, or it simply imports a block, eventually these transactions are going to be added at some point, and these add function will eventually be called, and this is called in a batch. So this is a list of transactions, and this is of type transaction, and inside one transaction struct there are some caches, but mostly it is about this time and this inner field, which is of type tx data. So TX data is an interface. So it's not hard coded what exactly it should look like, as long as it gives us these sort of functionalities. Okay, because there are various types of transactions. There is not just one type of transaction. So this interface implements TX type, copy, chain ID, access list, gas price, gas tip cap. So there are, gas price is obvious, but gas tip cap and fee cap, those you can set to enhance your chances of your transactions getting included in the blockchain. The nonce too. So nonce is the amount of transactions that has occurred from your account. 2 is where you are sending the transaction. So these all things need to be implemented for any transaction, and there are like 5 implementations of the transaction type. So these are the 5 implementations. So access list transaction, blob transaction, which I mentioned before, dynamic fee transaction, since the London hard fork, the legacy transaction, and set code transaction. I think set code transaction is this, EIP 7702 transaction. So set code transaction implements the EIP 7702 transaction type, which temporarily installs the code at the signer's address. So essentially you can make an externally owned account temporarily a smart contract account. So you have to use this set code TX struct. You have to use the set code TX struct for that case. Okay, so now we're back to this add function, and inside this you go over each transaction and maybe do some basic validation checks. So pool.validate TX basics, and what it does some basic checks, and then you eventually call this add TX locked. Okay, because I suppose you add transactions one after the other, and when you are adding it, there should be some sort of locking mechanism so that we are ACID compliant. So when you are calling it eventually calls this pool.add tx, and this add is the small a, and this add validates a transaction, inserts it into a non-executable queue for later pending promotion and execution. Okay, so we have 2 things in a transaction pool. One is a queue, another is a pending. So pending ones are just waiting to be included in the blockchain, where a queue ones are simply just queued. And if the transaction is a replacement for an already pending or queued one, it overrides the previous transaction. Okay, so here this is a function of around 140 lines of code, and here a lot of core logic happens for a transaction pool. So here it checks, okay, discarding already known transactions. So if transaction is already known, discard it, then do some validation checks. If it fails it, discard it, then check if the address is not yet known, exclusively track it. So there is a mechanism to track the transactions from particular addresses, so that if one address sends a lot of transactions, then there should be a limit. Okay, otherwise it will be easier to do DDoS attacks. And then if the transaction pool is full, discard the underpriced transaction. So this is one of the core logic. So the transaction pool itself, it has a limited size, but what happens if it is full? If it is full, the new transaction comes, but it has a very high, let's say, gas fee or something. So as a validator, you are more inclined to entertain the new transaction as opposed to keeping an old transaction that will give you much less gas fees. So in that case, you are going to discard an underpriced transaction and include the new one. Okay, so that sort of logic happens here. And what is this check? So here we are checking that all our current slots plus what extra slot our transaction is going to bring, if that goes higher than the total available slots. So why am I talking about slots? Why am I not talking about just the transaction numbers? Because different transactions are of different sizes. So the key way to measure a transactions load is by talking in terms of slots. So some transactions may take up lots of slots, and in Ethereum the data storage is done in terms of slots. So and one slot is of a certain fixed size. So here we have this global slot and global queue. Okay, and if the transaction will imply that this limit is crossed, then we have to actually try to discard any enterprise transaction. And that's a lot of not necessarily complex logic, but it can be confusing at times. So there are lots of checks that are happening here. So we are about to replace a transaction. We ensure we don't do reorgs too often, and then we call this discard function to find out which transactions to actually drop. So this is stored in this drop function, and then we actually try to drop those transactions. That thing happens here. So if we are trying to drop, this is the loop in which we are trying to drop those transactions. And once those are all dropped, then the new transaction is ready to be included. So then we try to replace an existing transaction in the pending pool. Okay, so in this loop, there was this loop will only get activated if it is actually we are hitting the limits. Otherwise, we will we're not hitting the limits. So we are happy to be including this transaction. So we are checking if it is replacing an existing one. Which means you probably send the same transaction with higher gas fee or something. In that case, you eventually add it. Otherwise, you simply do this pool.enqueue transaction. So any transaction goes through stages. So it is part of a queue first, then it eventually gets into the pending pool. So let me show you how this legacy pool struct looks like. So inside this legacy pool struct, okay, there's a long description. So this legacy pool contains all currently known transactions enter the pool when they are received from the network or submitted locally. Okay, so let's see what all things it has. So it has some config stuff. It has the blockchain, and it has this pending as well as queue. Okay, so pending is a map which has the transactions, and it has all currently processable transactions, whereas queue is queued but non-processable transactions. Okay, so a transaction has to go from queue to pending before it can actually be served. And what is this list? So list is a struct which has the transactions. So list is a list of transactions belonging to an account. So one account can send multiple transactions, but up to a limit. So it makes sense to store the transactions account wise. So in this case, these transactions are stored inside this list, and inside this is of the form sorted map. And in this map, what we're doing is we're storing hash map storing transaction data. Okay, so sorted map is a nonce to transaction hash map with a heap based index to allow iterating over the contents of nonce incrementing way. Okay, so here you can see this pending is a map from the address to list. Okay, so this is the address belonging to some particular person, let's say, and he has a list of transactions. So these two are the key components of this legacy pool struct. Okay, so where was I? I was talking about this add function. Okay, so this add function will get called whenever a transaction is supposed to be added. So that is one important function. And I was in the loop. Okay, so I think that's a good enough overview of how txpool works. Let's see some other things, which are, let's say, this evm.go. So not EVM, this, where am I looking? Yeah, this VM. So core has this VM package, and inside this VM I have this EVM struct. Okay, so EVM is the Ethereum virtual machine base object and provides the necessary tools to run a contract on the given state with the provided context. It should be noted that any error generated through any of the calls should be considered revert state and consume all gas operation. The interpreter makes sure that any errors generated are considered to be faulty code. So EVM is the Ethereum virtual machine, which is in charge of actually executing the transaction logic if you are simply calling a contract method. And this does a lot of stuff. Let me show you one of the more important functions here. So perhaps the most important function here is this call function. So this call executes the contract associated with the address with the given input as parameters. So if you're calling a smart contract function, it will likely end up eventually here, this evm.call. Okay, so this has this caller.address, the input, the gas, and the value. And here it does some basic checks first, and then let's say checks for if it is a precompiled contract. If it is not, then it takes the code, gets the contract, and then here it's the important bit. Here it calls the evm.interpreter.run. So this is the interpreter.run. So what is interpreter here? So interpreter represents an EVM interpreter. Okay, it could be more descriptive. So so what an interpreter can do is that you have a predefined set of stuff which it can do, and you simply ask it, okay, you first should do this, then that, and the interpreter will understand your understand what you are wanting to do and actually implement it. So just like a Python interpreter, similarly we have an EVM interpreter. And EVM, when the interpreter.run is called, let's see what it does. So okay, so it is called in the form okay, so it's called, and the inputs are the contract. So the contract is an Ethereum contract. The input here, so we have a contract, and this has information about the related function that is supposed to be called. Okay, so let's see where the input is called. So contract.input is input, and then there is a for loop eventually. So interpreter main run loop. This loop runs until either an explicit stop, return, or self-destruct is executed, an error occurred during the execution of one of the operations, or until the done flag is set by the parent context. So here the opcodes are executed. So any contract code, if you're writing a smart contract function, it will be eventually converted into a set of opcodes. So for example, okay, okay, bring the data corresponding to this variable from this part of memory, maybe add something and then store it back, these sort of basic instructions. So those are in the form of opcodes, and there are like various opcodes, like here we have all the opcodes.go, and you have stop, add, multiplied, sub. Right, so we get the opcode here, and we get the operation corresponding to that opcode, and then we eventually call operation.execute here. Yeah, and that's how the actual execution finally happens when you are calling when you want to execute something in the execution layer. Yeah, this is the execution we are talking about, to execute that particular operation. And this is of type execution function. Of course, it is of type function here, and these are whatever different opcodes have different execution functions. And then you get the result and you return the result. Okay, so EVM interpreter.run, that is called from this core VM evm.go. So this is one of the most important bits, one of the core bits of Go-ethereum codebase. And then what happens is, when an error was returned by the EVM, or when setting the creation code above, we revert to the snapshot and consume any gas remaining. Okay, so if there is an error, so it's a very critical thing that is happening. Okay, we have state of the Ethereum, the current state, and there is a transaction which is asking us to do something. While doing something, there's an error. We encountered that, okay, that's not going to happen. Then what we're going to do, we have to revert back to where we were before. Okay, otherwise we will end up in a corrupted state. So this is what we're going to do. So here we're checking the error was not nil, which means something wrong has happened, which is why we have to revert to the snapshot, so that we're undoing that thing. And then that is supposed to consume any remaining gas. Okay, so I think the revert to snapshot function does that. And then there is a to do thing. I don't know what that is about. Consider clearing up unused snapshots. Interesting. So revert to snapshot. And what is the snapshot? It was, we had created a snapshot. So it's like storing a copy of your DB, your state. And revert to snapshot, it has multiple implementations, it seems. So yeah, the state DB has an implementation, so it eventually calls the revert to snapshot. Okay, so now we have talked about the VM side of things, so the actual EVM, the execution side of things. Let me show you one other important file here. This is the state transition.go file, which has the state transition struct. And what does the state transition struct do? State transition represents a state transition, the state transitioning model. A state transition is a change made when a transaction is applied to the current world state. The state transitioning model does all the necessary work. Okay, so whatever we were discussing before, it will be upstream somewhere. State transition function will be doing it, and let's find out where exactly it is. Okay, so what all things it does nonce handling, prepay gas, create a new state object if the recipient is nil, value transfer. If it is about contract creation, attempt to run the transaction data. So one important function in here is that is this execute function. Okay, so execute will transition the state by applying the current message and returning the EVM execution result with following fields. Okay, used gas, return data, or if there is an error or not. So let's see who calls this execute function. So this execute is called by this applied message function, which is called by state prefetcher. Okay, it is called by a lot of people because state processor apply transaction with EVM process. Yeah, so this is one example of where it can be called. So process processes a state changes according to Ethereum rules by running the transaction messages. So let's see who calls this. Type state accessor. Blockchain.go also calls. So it eventually ends up here upstream. So process block executes and validates a given block. Okay, so when we receive a new block, I suppose this process block should be called. So let's check that. This is called here inside this insert chain function of the blockchain struct, which I mentioned before. So insert chain is the internal implementation of insert chain. Okay, so there is another insert chain, which where is it? Yeah, this is the one. Insert chain attempts to insert a given batch of blocks. So if you receive a batch of blocks from a peer, you need to insert it inside your own local blockchain, right? So that's when this insert chain function is called. It's a quite popular function, as you can see. Okay, so let's see where it is called. One of the important places where it is called is this downloader.go. Okay, so downloader.go is inside this eth/downloader/downloader.go. Okay, so inside the eth package, And here we have import, where is it? Yeah, import block results. So downloader is responsible for, I think it is responsible for listening to new block events and actually downloading, or whenever you are actually starting your blockchain, you're supposed to download the other blocks, and maybe that's where this downloader comes into picture. So let's see, import block results, which is called in, yeah, process full sync. And this is called from sync to head. Okay, so this is sync to head, which ends up here synchronize. So synchronize will select the peer and use it for synchronization. So whenever you start a block, a node, I suppose, then you're dependent on your peer. Okay, you don't have all the data you need to run the blockchain, so you are going to download the block data from a peer only. So this is when it happens. So you need to synchronize it with a peer, I suppose, and this synchronize is called from this resume starts the downloader for backfilling state and state data. This resume, okay, so yeah, you can resume or when you are starting up as well. So let's see, this downloader.go, let's see where it starts. So it must be, starting out at some point. So new progress, register peer, you're registering a peer at some point, and then it is calling synchronize sync to head. Fetch bodies is an important function, so which is also used inside the sync to head. Okay, so we finally end up here, something called skeleton.go. I don't know when it was actually created. Oh, it's been a while. Okay, so this skeleton, struct is has a function called startup, and the startup is an initial background loop which waits for an event to start or tear the syncer down. This is required to make skeleton sync loop once per process. So at some point a startup function gets called, inside which there is an expected infinite for loop in which you are listening for head events, and then you have to do the corresponding syncing. Okay, let's see where the startup is called. This startup is called new skeleton, and yeah, okay. Whenever you are creating a new downloader, you are already starting up the syncing process, and then you're also calling the state fetcher. So a lot of things you have to fetch from a peer. One of them is the blocks, the transactions, and the states. So those all things are done whenever you are starting your node. And let's see who calls this new. So this new is called from this handler.go. Okay, and this is part of this new handler function, which is called by this backend.go, which is inside this new function. New creates a new Ethereum object, which I think we saw this before, and this is called by register each service, and this register each service is called by this makeFullNode. Okay, so we are back to where we started. Okay, so you are seeing like how a lot of things are being coordinated from the start. So the absolute start was just this make config node. Like there are like just two functions. Yeah, so we just started with this Geth function, which only had this, okay, make full node and start the node. That's it. But we are seeing like downstream, there are so many things that are starting up. Okay, you are like, you have transaction things, you are things like downloading, syncing, and then listening to transactions, eventually executing them if it is needed to be executed. Um, so yeah, let me see. Let's get out of this command. I have gone through the core. ETH, we have gone through a little bit. The DB one I can maybe cover at some other point. Let's see P2P. Peer. So the P2P is responsible for discovering your peer as well as exchanging information or messages from the peer. And there's this concept of handshaking. So you discover it, there is a handshake message. There are various other types of messages as well. Okay, there is this file called server.go inside the P2P package, and there is a start function. So start starts running the P2P server, I suppose. And yeah, so it is in charge of all the stuff related to P2P. So let's see who exactly is having this downloader. Yeah, downloader is part of this handler struct. Okay, so handler is just ETH slash handler. So handler tx fetcher. So so downloader and tx fetcher. So this handler struct has at least two very important things, this downloader and the transaction fetcher. It also has this tx pool database. So this handler is part of this Ethereum struct. Okay, so this is kind of hidden here. So this looks like a very small field here, but it has a lot of stuff going on. So inside this handler, we have this database, tx pool, the blockchain struct itself. But what I have showed you is this downloader, and what I have not showed you is this tx fetcher. So transaction fetcher, what it does. So it is responsible for retrieving new transaction based on announcements. So when new transactions are occurring, or if you are receiving a new transaction, what happens is you might end up announcing the transaction. You do the same for the blocks as well. You announce them so that your friends, your peers also listen to them. Okay. And then this fetcher, this tx fetcher actually does the fetching. And let's see, there's this notify function to notify announces fetcher potential availability of new batch of transactions. So it probably notifies the peer, I suppose. What else? NQ. So NQ imports a batch of received transaction into the transaction pool and the fetcher. So who calls the NQ? NQ is called at handle. Handle is work to ETH. Okay, so essentially I think you are listening to whatever new transactions your peers are sending. You're listening, then you're actually handling it. Okay, so that's where this handle function comes into picture. And we were at this NQ thing. So NQ, inside this NQ, let's see where these transactions are ending up. So here there is a for loop, and we have this, we're eventually calling this underprice.add. Okay, so I talked about this handler thing. So when the handler is created using this function new handler, there is this type, there is this variable called add transactions, which is like a callback. So it is a function. If it is called, then h.txpool.add, we are adding the transaction inside the tx pool. Okay, so that add tx, that ends up inside the fetcher at some point, because whenever you are creating this new fetcher. We have this add functions which becomes part of the fetcher. So the fetcher will call this add transactions at some point. Okay, so the fetcher didn't have to store the entire tx pool itself. Rather, it just has a callback function which will get executed if it wants to simply add a transaction. Okay, so this is connected all the way to the transaction pool through this handler. Okay, so this I talked about what transaction pool, execution stuff, P2P stuff, the command stuff where it all starts. I did not cover the state DB or the DB specific stuff, which I can talk in some other video. There's just one piece remaining, which is the consensus side of things. So the actual consensus does not happen inside inside the execution layer itself, but rather the consensus layer asks for execution payload from the Go-ethereum. Okay, so let me show you very briefly how that works. So whenever there is a time to create a block for a validator, then the validator asks the execution layer to give him the actual execution payload, and that payload is asked for through this engine API. Okay, so I think it is called execution payload. Get payload engine get payload v4, let's say. So there are like multiple ones. Okay, you see here this consensus API will use this API function, so it's get payload v4. Okay, and call this function to actually get what will it get? It will get engine.execution payload envelope, which has the executable data and blobs. Okay, and what is this data? It is the execution, it is the data necessary to execute an execution layer payload. So this has the typical block stuff like parent hash, state root, the random gas limit. It has all the transactions, the block hash, base fee per gas, the timestamp, obviously, excess blob gas. And we have a separate entity for blobs. So blobs bundle, blank blobs have commitments, proofs, and the actual blobs, which are of the type bytes. Okay, so what I showed here is get payload v4. Okay, so this will be called from the execution from the consensus client. And let's see, I will show you the corresponding place of the consensus layer where this is more likely will be called. Okay, so I'm in this Prism repository now. So this is Prism, which is the Ethereum consensus implementation. So now let's search for engine payload v4, right? So here it is there. So new payload method v4 is the engine new payload vx method added to Electra, and this new payload method v4, that is obviously is going to be called from somewhere, right? So here this is where this RPC client is actually calling the execution layer, and this is called from the new payload. Okay, new payload request calls this via JSON RPC API. So new payload is called whenever there is time to create a new payload to create a new block for a validator. So this new payload is called from okay, maybe in some other video I can talk about how Prism works or how the consensus layer works. But for now, I'm just trying to show you, at least one example of how execution layer and consensus layer are actually connected through the engine API. Okay. So this was a relatively deep dive into the Go-ethereum codebase. It was heavily unstructured. I did not plan for it. I just thought, okay, let's do a deep dive because some of you asked me to do it. And then, yeah, I hope you enjoyed it. If you have any questions, please feel free to comment. And if you think I missed something important or if I said something wrong, please feel free to clarify that as well. And let me know what other kinds of videos you would like me to make in the future. Thank you.